I'd like to devote today to learning about Kirchhoff's rules for circuits. Kirchhoff's rules are probably the most important thing with circuits, especially as the circuits become more and more complicated. Okay, so Kirchhoff was from Germany, and in the mid to late 1800s, he came up with two rules that apply to every single circuit. Okay, so by learning these two simple rules, we can analyze a circuit no matter how complex that circuit happens to be. These two rules are going to center around junctions and loops. Okay, so the first rule is the junction rule. The second rule is the loop rule. What do I mean by a junction? A junction is where you have multiple things joining up with each other. Okay, so we could have three wires that are all joined together at a junction. We could have a resistor hooked into a light bulb. That could be a junction. Junctions are where things join. Loops. A loop refers to when you make one complete trip around the circuit. That is called a loop. So we have a junction rule. Certain things are going to happen in every single junction in your circuit, and something else happens for every single loop that you can draw in your circuit. All right, so let's look at them. Starting with the junction rule. So let's make it simple. Let's say we have three wires that are joined up at a junction. Here's our junction again, a little circle. Let's say the electrons are flowing this way, and let's say there are 3 amps flowing into the junction. Let's say at this spot we have electrons flowing into the junction of 7 amps. Kirchhoff's junction rule says that this current has to be 10 amps. He says whatever current enters a junction has to equal the current that leaves the junction. Why is that? Because remember, 3 amps means 3 coulombs per second go into the junction. 7 coulombs per second go into the junction. These coulombs can't just disappear. We have the idea of conservation of matter. We have conservation of charge. Okay? These coulombs must emerge from some other spot, and the number that enter has to equal the number that leave. Junction rule. It is true for every single junction in every single circuit. How would we apply our junction rule? Well, let's say we had a parallel circuit like this. I'm just going to make up some numbers. Let's say we calculated our current in the top branch and it came out to be 10 milliamps. We calculate our current here, and let's say it comes out to be 8 milliamps. And we calculate our current here, and let's say it came out to be 3 milliamps. Again, it's not consistent with the resistor shown. I just want to give you the idea of how this is going to work out. Okay, so we have 10 milliamps flowing this way, 8 milliamps, 3 milliamps. How much current entered this junction? So all you would do is you take the 3 currents that are leaving the junction, add them together, and we should get 21 milliamps going into that junction. We could also look at it here where we have 10 milliamps from the top branch, 3 milliamps from the bottom branch, 8 milliamps from the middle branch. Here's our junction. These are all going into the junction, so we need to have 21 milliamps coming out. What goes in must come out. 3 coulombs come in, 3 coulombs come out. That is our junction rule. Now with a series circuit, it's super easy because every junction only has one thing going in and one thing going out. So if we look where R1 hooks up with R2, whatever goes into the junction from resistor 1 must come out of the junction and go into resistor 2. So Kirchhoff's junction rule is why in a series circuit, all of the currents are equal. Okay, the second rule is known as the loop rule. So I want to take a moment and make sure you understand again what I mean by a loop. You can start anywhere you want in your circuit. I'm going to just start here because it's the spot that's closest to me. A loop means I go through my circuit and I make a complete loop, meaning I return to the exact same place I started. And what Kirchhoff's loop rule says is that the change in voltage that I experience for any loop is going to be 0 volts. You could also think of it, if you add up all your voltages, you're going to get 0 volts. So what does all this mean? Okay, so you got to remember that voltage is actually a measure of energy. So this 12 volts means that the electrons are going to gain 12 joules for every coulomb worth of charge. Okay, so inside the battery, they gain 12 joules of energy. As they flow through the resistors, they're going to lose 1.2 volts, they're going to lose 5.5 volts, they're going to lose 3 volts, and they're going to lose 2.3 on the last one. So if we add up what they gained in the battery and what they lost in the resistors, we should get a total, taking into account the pluses and the minuses, of 0. If we just look at the energy we started with and the energy we end with, we should have a difference in energy of 0. Okay, this is true for every loop in every circuit. You gain energy in some spots, you lose energy in some spots. When you get back to where you started, you need to have the same amount of energy. 0 gain in energy, 0 change in energy when you get back to where you started. Think of it like you're on a certain spot on a mountain and you want to get to the top of the mountain. You're going to gain potential energy on the way up and you're going to lose potential energy on the way down. When you get back to where you start, you're going to have the same potential energy that you started with. You're in the same location. Realize you don't have to go straight up the mountain. Maybe you take a more circuitous path to the top. You still gain the same amount of potential energy. You still change by the same amount of height. And then you come back down by a totally different path. No matter how you take this loop, no matter how complicated the loop, when you return to where you started, you're going to have the same potential energy that you started with. Okay, so your net change in energy is 0. Okay, I want to look at this one more time just to make sure you're good now. So in the battery, it's like you're climbing the mountain. In the resistors, it's like you're coming back down again. You're gaining energy, you're losing energy. When you return to where you started, you're going to have the same energy you started with, so your change in energy is 0. Okay, so again, inside this battery, every coulomb is gaining 12 joules worth of energy. In this one, we are losing. As we go from one side of the resistor to the other, we lose 1.2 volts, meaning when we emerge on the other side, we are down to 10.8 volts. 10.8 joules worth of energy per coulomb. Okay, when we pass through this one, we lose another 5.5. You can call it volts or you can call it joules per coulomb. So we take another 5 away and we're now at 5.3 joules per coulomb. We go through this resistor, we lose another 3. We're down to 2.3 joules above where we started. And then finally, when we're here, we're down to 0 joules. How do we get through the rest of the wire? Because we're assuming these wires are ideal and don't have any resistance in them. So we don't need any energy to get through this. It's like sliding along a lake that is frozen. Okay, we're not going to be losing any energy as we move through this wire. Now again, real wires are going to have a little bit of resistance, so we will lose a little bit of voltage in this wire, but that will be accounted for by a little less voltage we lost other places. We still have to lose all the energy that we gained in the battery. Okay, so with Kirchhoff's loop rule, if we take our loop, we'll start it here, and we'll loop through the battery. Let's say it's a 9-volt battery. We gain 9 volts. We flow through our meter. We go through the top branch, and we get back again. We have now lost 9 volts. We gain 9, we got to lose 9. If, however, we took the different path, we gain 9, we lose 9. So this shows us why in parallel circuits, every branch of the circuit is going to get the voltage of the battery. So again, 2 simple rules. Loop rules, which say whatever energy we gain in a battery, we're going to lose as we go through our different components. It might turn into heat, it might turn into light, it might turn into sound, but we're going to lose that energy as we make a complete loop through our circuit. The other rule talked about junctions, and it says whatever charge enters must be equal to the charge that leaves. Super simple rules that can be used to help us solve really complicated problems.